programming. One is going to be about depletion force. Second one is about well, injecting bias into machine, which is more related to Anglican programming language and probabilistic programming in general. And third one is going to be about the church programming language, which is a predecessor of the Anglican. And I will let Stefan start with the talk about the depletion force, and we'll continue in the Reihenfolge.
Okay.
Yeah.
So yes. Please do your magic.
Yeah, that's
so they can see it. Ah, okay, great. Yes, great. So I will tell you. I'm Stefan Schwetschke, as you can see there. Oh, and it shows automatically all my slides. That's not too bad, because I only have 3 of them. And it was quite spontaneously that I decided to give the talk. So I drew them tomorrow at 5 o'clock, today at 5 o'clock in the morning. And so I hope I didn't mess up too badly. If there are some big mistakes, so just ignore them. And yes, this you can reach me at my private email address. You can find me on most things with my handle, Gecko98. When I was young, it was cool to have a number in the handle. It is a little time in the past, but I hope it gets cool again, so I won't change it at the moment. And yeah, and I will tell you.
That's your birth year, right?
No, not really. I'm a little bit much more older than this could be my birth date. No, it's papers. It's a paper lavas here, but it's on a Coursera course, so it's more a video. I laughed, but I think it's okay here. And it's from statistical mechanics, algorithms, and computations from Werner Kraut. And I think it's still on Coursera, so you can see the whole thing. What you can see here is only 1 chapter in this Coursera course, what I got from there. And it's basically what we had to do there as an exercise. We also had to write some Python code, but I couldn't find it, so I can't show it you. So you have to do it yourself, the simulation that is behind it. And the depletion force, it's a nearly natural force, so like gravity and so on. But it's a force completely caused by statistics. So if you would assume, some people say, oh, perhaps we live in a simulation and so on. So gravity would be a parameter that you have to put in and so on. But the depletion force is, as soon as you have randomness and boundary, you have the completion force. You have the depletion force in it. And so it wouldn't, they couldn't do it out of the simulation. It would be just there. And even if you do some simulation on your computer, some Monte Carlo simulation or something, you will observe this natural force. It will be there, and you can see it. And I will show you. When I learned it in the course, it totally blew my mind. And I hope I can bring this over to you. So you can say also, oh, this is really, really cool. I'm glad I have heard it. Okay, so you see the slides are, we are now on the left side here. You see this thing here. You can imagine it as some kind of solution. And in the beginning, there are these red particles in there. And these particles, the only thing we have to know about them is that they can't overlap, like it's usually for particles. And they are swimming there and are completely driven by statistics. And they're just with Brown in motion, and they're just floating around and are evenly distributed. And then we put in this big black particle. And as soon as we put it in, we see that it starts to attract these red particles. You will see that here there will be fewer of them, and they will gather around this black particle. And if you have some way to remove some boundary around these black particles, you can also decrease the concentration of the red ones. And people who saw this were amazed and wondered, oh, why is it gathering these particles? Perhaps it's pushing them around, or perhaps it has some sticky surface or something. But no, it's completely driven by statistics. It's directly from statistics why they are gathering there. And so this attraction force you have there, you can also have it in your computer. You won't observe gravity in your computer when you don't put it in the model as a parameter, and you won't see the electric forces in your computer, but you will see this attraction force if you do some simulation. It will just be there. And this is quite great. Even if you imagine some stuff randomly, okay, it's hard to imagine something randomly, but even your thoughts will be subject to the depletion force to some degree. It's a natural force that works on information. And okay, so with this quite complex thing, it's hard to explain how it is working and why it is working. So we can simplify it a little bit. We in the Coursera course, they said, okay, we have three-dimensional particles. Might be some balls we have, but this is quite hard as a model. Then they said, okay, let's imagine them as disks that interact somehow, that interact randomly, but it's still quite hard. So they said, okay, let's see, we have some line here, and we put some clubs on it. You know, clubs where you can hang your clothes on to dry them. And you have then here these kind of clubs here too there, or we can just imagine them as some kind of boxes that are there. And they can be distributed on this line like you want. You can just take any random configuration there on this line, how you put them on the line, and each of this configuration is evenly likely. So this one is just one example you see up there. There could be any other configuration, and they are all evenly likely. But if you put a lot of these and you put a distribution about the center of each box, you see there are a lot here on the margin. And then you have this, then here are more, here are more, here are more, and here again on the margin there are a lot of them. So they are not evenly distributed. And this is strange if you look at it. But it can be very easily explained. And it can be explained when you look on the box. This here, this red one, is just this box. And we formalize it a little bit. We have here the center of the box. The center of the box, you see here is a more abstract one. Then we have here the core of the box. This is the core of the box, but the box has a shadow. If the box has a width of sigma, it has a shadow of sigma half, we say. The green one is the shadow. And the next, here again, here's the more abstract one. We have the center, we have here the core of the box, and we have the shadow. And when we take another box, we can say the center cannot enter the core of this box, but it also cannot enter the shadow of this box. Okay, so easily, but the shadows can overlap. Somewhat clear, this construction? See a lot of nodding. I hope you are not just polite, but really understand what I want to tell you, but okay. And when we put these boxes one beside the other, then into the shadow, no other box can be in, no other center can be in. So you can imagine this shadow is some kind of death space when you want to say it like this. It's some wasted space, we can't use it for anything. So I have here a very wasteful configuration. We have here the shadow of the border. Again, here in the shadow, no other box, no other center can go in, because then it would the core would collide with the margin. It doesn't work. And then we have this box just so wide there that its shadow just overlaps a little bit with this, so we can't bring another box in it. I hope I drew it correctly. So this must be so narrow that I can't get another box in it. And here the same, not nearly sigma is the distance here, nearly sigma, so I can't bring another box in it. And so I have wasted a lot of space here. Here you see a more compact configuration. With this configuration we have less shadow, also two boxes but less shadow, and we could just push it a little bit more to the border, then we have evenly less shadow. And now comes the interesting part of it. The ones where you have less shadow, they have more degree of freedom. You have more possibility to put other boxes in here because there is less area inside the shadow and you can't put another box in such a shadow. You have less shadow because the shadow can overlap but the boxes can't overlap. And less shadow means more degrees of freedom. And more degree of freedom means there are more configurations possible. There are more possible configurations in this case as in this case, because here we wasted a lot of place that we could use to generate other configurations. So even when each configuration has the same likeliness, it's evenly distributed, each one can be the same, there are simply more that are of this kind than of this kind. So if I draw some randomly, it's more likely that I get such a thing, or better, the one where I won't even have this shadow, where I'm inside the shadow, there are more of them, so it's more likely to get such a configuration. And this explains that. It's just that I have more configurations of this kind. And this leads to this effect that the boxes seems to attract each other and that the margin seems to attract the boxes. Okay? So not so much people are nodding. Okay, I seem to have lost some of you. So some question at this point?
No, why do you say that I cannot have the same in the middle?
We the same in the middle?
Yeah, if you take a spot in the middle.
Here?
Yes.
Yeah?
There you can have the same.
Yeah, of course. But I have, when I do such a wasteful configuration, I have just fewer space than in this case. I just have more space where I can put something in. It is totally possible to have some in the middle. There are just not so much if I have wasted the space. If I have free space, then there are just more possible configurations. And if each of the configurations are evenly likely, then it's more likely to get one of this kind because there are simply more.
Yeah, but I'm not getting those kind only on the left side, but on the complete string.
Yeah, so you can do.
What is the argument for saying the likelihood of having compressed boxes are at the left and right end higher than in the middle?
No,
it's
not it's hard to formulate it correctly. It's just the idea of it is when you have more degrees of freedom, you have more possible configurations, and of course they are all same likely. It's no problem. Each of these configurations, a wasteful configuration, is just as you can just draw a wasteful configuration or other configuration. There are just more of this, where some of them are compact, than are of this kind. We have wasted a lot of.
Yeah, but nevertheless, I can put them randomly over the string.
Right, you put them randomly, and
why is it then more to the left or more to the ends of the string?
No, it's more.
Sorry, I think if you put them in the middle, you become less flexible about how much you can put left on right.
You have less.
Think of the trunk of your car, right, and think of packing it. You're probably going to put things in a corner and then you're going to start packing.
So it's less likely because you have wasted more space, and this means there are not so much configuration of this kind. If you put them more compact, you have more degrees of freedom for the rest. If you put some of them more compact, you have more degrees of freedom for the rest. It's just the argument.
Do you start putting the boxes from the sides?
No, you just put them randomly, and from the idea, if you would make it as a simulation, you throw them there randomly, and if they overlap, you throw it away, and if you don't overlap, you keep it. This is just the one what they're doing.
But do they have dynamics? They are moving on the string?
Nope. It's the idea of this kind of simulation is that if you make a very dynamic simulation, or you just put them randomly, it's just the same. If you would imagine it as a stop motion picture, as a stop motion movie, it's just scrambled the pictures. But this would be another story. It's part of a simulation, and you can just put one randomly or make a complex simulation, and statistically it's the same, you get the same result.
So you are really saying that I generate, so between 0 and 1, I generate the centers of the boxes and I just reject those that are too close?
Right.
You get the bimodal.
Yeah. And there are even better algorithms for this that lead to the same result, exactly the same result. You can even prove it, but you have to watch the Coursera one, or we have to make a different call because it would totally be beyond this talk.
Is the graph the summary of all possible configurations?
Please?
Is the graph?
Yeah, this one is
summary. Is that the summary of all possible?
This is the likelihood of all the possible configurations. Of all the possible configurations.
Because of all possible configurations tending to the edges.
Yeah. So you have more. It's more likely to have one where they are on the edges. Or if you would do a Monte Carlo simulation, it's the amount of one where you have it there. Any more questions? Oh, yeah, thanks.
Does it depend on the construction being iterative, like you put one box at a time and fill up those spaces that are still left, or would that also happen if you kind of chose from the micro ensemble directly?
That's really hard. The idea you say is you just put one box and then you use the rest. This would lead to a wrong result. You have to put them all at once. And then look if you can reject it. There is an algorithm that looks like what you want to do, but it's a little bit more complicated.
So it does not depend on that.
It depends. If you won't observe this, but you won't do a statistically correct simulation. If you put first one box and then you only use the leftover space.
It doesn't do that, right?
It only works if you put them randomly there and throw away the overlapping ones, or do an equivalent algorithm, which is a little bit more complex but leads to the same result. But you just can't.
You sample all the boxes at the same time and not.
Yeah, you throw them in there all at the same time, or do something equivalent, and then you throw away if you have an overlap, and you keep the configuration if there is no overlap. You have to do it this way. Otherwise, you get a wrong statistical result.
Okay, I just wanted to clarify.
Yeah, but it's a very, very good point, a very good observation. Okay, so when you got this, I just have one final one where I can just show you something. You can just observe it. Imagine you have some diagram and you want to you have some boxes with different size, and for example, you want just put them randomly on to generate a diagram that looks good, and you just generate some of them randomly. Just put them in on the sheet and look what comes out, because you don't want to arrange them all by hand. You just make them randomly until it works fine. And then if you look on these random configurations you do there, if you do it right, you will observe something strange. It will look like the big one attracts the smaller ones, and the corners attracts them all. So the big one attracts this one and this one attracts these one. They are clogging together, and this is the depletion force you see without introducing them. You will just see it. They will clog together, and you will very likely see them on the corners, and you have lots of configurations and always they are clogging together. This is the reason for this, and you would have to introduce some artificial compulsion force that puts them out, that puts them away from each other. You have to add it artificially to work against this depletion force that works like gravity, and it's just there. And now you perhaps can even imagine why, because perhaps you can imagine the shadows around these boxes, and you can imagine which configurations are more likely and which are less likely, where I have more degrees of freedoms and where I have less degrees of freedom. And without introducing any forces, you will just have it here. They will just, if you take some random sample, it will just look like they clock together. And you will just think there is some gravity or something, and you have to introduce some artificial repulsion force to get a nice looking diagram. Okay? And that was it. Thanks a lot.
Thank you, Stefan. It was very nice.
Yeah, you're welcome. You will need this?
Yeah, well, everybody needs this. Eventually. So yeah. How does it work? I will try to be as short as it is possible. I think it's going to be roughly 30 minutes. And let me put myself on a timer before So 30. Okay. Yeah. So I work here in this Glaskasten for the company which is called Instana. We are a spin-off from CodeCentric, and we're doing application performance management, and it's also like we do lots of analytics, and that's why like one of the reasons we got like lots of ideas with probabilistic programming, and we kind of experiment with it a little bit. And mostly I'd like to talk about the anomaly detection, and because the anomaly detection is something where the something like probabilistic programming fits at best. If you attend my talks, probably you may have seen that slide. So anyone read Antoine de Saint-Exupéry? If yes, you should see the elephant being swallowed by the snake right over here. And obviously, these are just some graphs of, well, some CPU anomaly. Let's say your server got some burst of like maybe DDoS attack or whatever. So there was some event that could be also interpreted as an elephant, although it was just a burst and it's just an anomaly. And we as humans are very good in detecting anomalies. And we're gonna talk about it more today in how we detect anomalies and why we have biases and what we do with our biases. And we're gonna talk a little bit about the statistical models. So statistical model is consisting of the two parts. One part is the observations, and the second part is the probability distributions based upon the observations. Because otherwise, if they would not have been connected, it would be well, unfortunate, if not to say more. And we're going to talk about the Bayes theorem, because that's a base for everything which is related to the probabilistic programming. And it looks like that, of course, and so it's basically interpreting the posterior probability based on the prior probability and the likelihood. And the example or the intuition, at least for me, for the Bayes theorem is based on something which is called naive Bayes, which is one of the simplest classification algorithms which you can build upon the Bayes theorem. And I tried to make it as intuitive as possible, so my 6-year-old daughter can interpret the Bayes theorem these days. I mean, and she said it's okay, people understand that. And I mean, she said she understood it, no problem. And basically, if you would like to calculate the probability of the star being blue, you would have to calculate the probability of oh, I'm sorry about that. I just need better formulation. Of the stars which are, or of the blue dots which are near star, which are in proximity, let's say, of the star, multiply it by the amount of, well, oh, sorry about that. I thought I would be more fluent with that. Amount of the, well, things which are within the star itself, and divided by the probability of the blue in general, and probability of the blue in general is the total amount of things divided by the amount of blue things. And if you put all these three things together, it would be obvious that total in the proximity of the star is going to be repeated twice, once on the top and once on the bottom. And the same thing is going to be happen with the total amount of the items. And we will end up with just having the amount of blue dots which are near the star divided by the amount of the blue dots in total in general. So that would be how we would well, take the Bayes theorem and apply it to a classification problem, and well, pretty much boil it down to the posterior probability, well, which is calculated from the prior multiplied by likelihood and divided by the evidence. And the evidence is something that we have experienced. So we basically know how many things are in total. We know which are blue and which are red, and we can kind of like classify other things based on whatever we have seen. And now I just need one volunteer who would play the game of number guessing together with me. Who would it be? Anyone? So yeah, please. Sorry, he was first. So I say you the series of numbers. It's like 2, 4, 8. You should guess the what is the sequence. So you can ask me, for instance, like whether the number that you have in mind is belonging to the sequence, to that set. I will respond to you with yes or no. And you have as many attempts as you like. And in the end, you have to correctly say what is the secret behind this Reihenfolge, behind it. Huh?
My favorite game.
Yeah, your favorite game. So 2, 4, 8. Ask like which numbers are in it.
Is 1 in it?
1 is not in it.
Wait, did you say?
So let's say the next number. Okay, following 8. Following 8.
Following 8. Okay. 9.
Yeah, it is.
Okay. 10.
10? Yes, it is. I'm sorry about that. I had to think about it. Yeah, it is.
27,023,000,023.
Yeah, it is also.
Could any one of these numbers follow the game?
What do you mean, anyone?
So is it
like the
sequence, or is it a rule?
It is a rule. I have a rule in mind. Yeah.
Okay.
So the next number is based on the rule.
-2.
-2 can't be. Can't be after 8. Cannot be after 8.
So I'm fairly confident it's increasing numbers.
So it's the number which is larger than 8. Okay, you won. You can have a beer. Actually, well, I just failed miserably. Obviously, I miscalculated that. Well, the crowd that is gathered here is much more advanced than, well, because usually when you run this experiment with just, well, let's say random people, you get the answers like, yeah, I don't need to even ask you anything. I can say you outwards that it's all even numbers. I say, well, it's not all even numbers. It's like more than even numbers. Then they say, okay, it's then powers of 2. I say, no, it's not powers of 2. So basically, the idea behind it is that humans are biased toward induction. So whenever we see some pattern, actually I hope that whoever gets this question asked, he will say, yeah, it's going to be like 16, and then I like say, okay, biases, you say, but it didn't happen. which only makes it better, right? I mean, but you can run the experiment with the random colleague or whoever and see it. Sometimes it works, obviously not all the time. So humans are biased towards induction, and whenever we see some pattern, we instantly can recognize it the same way as the little prince could have recognized the hat or the elephant instead of the hat. And the problems that we have here is that we have somehow built into our brain the priors, which are our biases, so the things which we know about things, and the hypothesis spaces, which are basically the things that we know. For instance, my daughter knows about like the numbers. She knows that there are even and odd numbers, numbers that are larger and smaller, but she doesn't know about powers, or she doesn't yet know prime numbers. So, I mean, she knows already, but it was like also based, right before the talk, I started like probing what kids know in the first class, and I had to explain why I asked the question. And the hypothesis spaces is like, for instance, odd numbers, even numbers, and we know certain things about each one of these categories, and we can or cannot, based on our intuition, predict whether certain thing is going to fall into one of the categories. For instance, can any one of you instantly say whether 5,231 is a prime number? So it's pretty hard. So at least you have to think for a second. But if I ask you if 25,664,012 222 is even or odd? Can you answer that? Yes. Obviously. So you see that we have intuition, so we can instantly say things about things because we know like the patterns. And how do we embed or try to teach the machine to be biased towards certain things and look at what happens if we insert biases into the machine? So if you ask humans on a larger scale than just one person, and you run an experiment and start asking people to, you tell them the number and they start telling you which numbers are going to be following that number. For instance, you just named them the number 16, and they say, okay, the numbers which fall together in one category together with 16 could be, well, obviously the powers of 2 are outstanding, like 2, 4, 8, 16, 32, 64, 96, and so on. But you also see that since you named 16, like things are started cluttering, so around 16, so everything got dense over there. And if you set the first number instead of 16, 60, like you see that, for instance, like 20, 40, and like many numbers which kind of follow the same pattern intuitively are going to be named, for instance, even numbers, but also the numbers which are around 60 are going to be named more often than the others. But suddenly, as soon as you start saying the sequences such as 2, 8, 16, and 64, which follow a certain, let's say, stereotype, people start biasing themselves towards like powers of 2 in this case. But, well, just because you had a high prior with 16, it's still going to give some weight to it. And if you start with the numbers which have no apparent sequence, which are 16, 19, 20, and 23, it would be harder for the people to try to put them into some box that they know, so they won't try to classify it. They will just guess around what the information which they see, which is going to be some number which is around 20, because 20 and 16 and 23, 20 is, well, 19 is somewhere in the middle, but 20 is right next. So, but how do we bias the machine? The first way to bias the machine would be to use minimum likelihood estimate and the direct measure. The direct measure is a very simple thing. It's either saying yes whenever the whenever the element is a instance of a set, and says no whenever it's not. And for instance, we have a number, once again 16, which has been observed, and these are our priors, this is our likelihood, and this is our posterior. And obviously, like just in case with 16, the likelihood and posterior will be very similar, with an exception of, well, more complicated, so let's say very improbable things. This would be kind of not existing anymore after the after we have observed it. They won't be present in a posterior. And here we have like whether the thing is even. So whether something is even or odd, there is, well, pretty much 50-50 chance of that, right? And then we start adding like the different patterns we know. We have like whether it's a square, whether it's a multiple of 3, 4, 5, 6, 7, 8, whether it ends with 1, 2, 3, 4, 5, 6, 7, 8, 9, and whether it's a power of 2 till 10, and whether it's one of any numbers. Which is like obvious. And then we feed it with the data. So we feed our model, which is based on the maximum likelihood estimate and direct measure, and we feed it with the 2, 4, 8, and 16. And obviously, after that, our model is going to be so biased towards the powers of 2 that it would be impossible for us to convince our model that no, wait, it's just the next number. It could be any number, actually. But our model won't believe us. So data will overwhelm the prior, despite the fact that we had, well, exactly same probability for all the things. The data was so overwhelming that it outweighed everything that we imagined before. And let's model further how we specify or improve the model that we have right now. Let's try the even more complex prior. And one of the options would be the Bayes model averaging, and it would be looking something like that. Here you have like powers of 4, powers of 2, ends in 6, squares, even, and so forth. And the dots that you see here are just instances. For instance, if something is power of 4, there's going to be a dot here. If something is one of every number, it's going to be a dot here. So obviously here you have many dots. And here on the side you have weighting. And weights are usually based on whether or not or how probable certain thing could be. Well, it's very probable that something is any number, or some number is any number. It's like 100% probable, right? And so we would say that the weight of whether it belongs to all is negligible. It's very low. But whether it belongs to the power of 4, like if it does belong to that set, we should give it more weight, because obviously something less probable has happened. That's why we should kind of say that, well, when less probable things happen, we kind of give them more weight. We think that that shouldn't have happened, and it happened, then it's really, it can be like, I'm blessed now, or whatever. So at least you hear that in the news all the time, right? Also, this is also related to the black swan paradox and to the well, things that are making the news cry about all the things. So, but obviously, after we build everything against that model, we still have the powers of 2 outstanding. So they are still given the larger probability, so posterior probability. Well, their posterior predicted distribution, in that particular case it's even called differently, is higher than for, well, many other numbers. But you see that the other numbers haven't completely lost their value. Let's go even further, and it would be the beta binomial model. And with the beta binomial model, we can well, model some things which are called hierarchical Bayes models. And in order to imagine it in a better way, imagine that you have many coins that you're flipping. And the D with the index I is going to be how biased the coin is. So basically the it's Z coefficient. And well, it's going to indicate its bias and its tally. So how many times the heads are coming out, which is, well, essentially the same thing. And we need to calculate this integral in order to build a successful hierarchical Bayes model. And the problem with that this operation could be extremely costly. And in order to, well, let's get to how to solve the cost problem just in a second. But what the hierarchical model could do, actually, it could behave in a way which is extremely similar to whatever you see with the people. So I've indicated, okay, this is predicted, but I also have humans right on the next slide. And you see, if I click real quick, you see that there are slight differences in somewhere, like for instance here, they disagree. And also I have to specify that in the predicted, we have filtered our, well, Tenenbaum. It was not me making this picture, obviously, but the author of the paper, the Tenenbaum, he has filtered out all the things which are like, if it's not present in the human data, it won't be present in the predicted data either, just for clarity. But don't worry, it was not that the data which was filtering out was completely overwhelming and was like saying completely different things. So it's actually pretty good. It's just filtered out for the clarity. So what you see here is that the predicted values actually agree with whatever humans would think very well. Although, in order to calculate it, as we just spoke, you have to know the value of this integral. And in order to solve it, you would have to spend like lots of power, and sometimes it's also impossible. But you can approximate it with the Monte Carlo, with MCMC simulations. So then MCMC is consisting of two parts. The first part is Monte Carlo, and the second part is Markov chain. And the Monte Carlo simulation represents a probability distribution by the set of samples taken from it. And it is also supported by the law of large numbers. Anyone knows what law of large numbers is? So pretty much, well, many people do, but just let's recap. And if we have a coin, I was trying to throw it, but I fail like every other time, so it would be unfair to toss it like 50 times in front of you. I would embarrass myself. But if you toss the fair coin, like 50-50, which has a 50-50 chance of heads or tails coming out, you would get a picture which is not exactly like that, depending on how good you throw, but it would be most likely biased towards heads or towards tails. Why? Because you have tossed only like 50 times. It won't always come up 50-50. So it won't be like heads, tails, heads, tails, heads, tails. And even in that case, like if it was coming out like that, if you would throw the odd amount of times, then it would be still unfair. Then you take a larger number, but now we have an unfair coin, like the coin which is coming up heads less amount of time. And we see that the pictures are actually looking almost the same. So 28 and 28,000. So the fair coin, given the small amount of tosses, is going to look exactly like the ridged coin. And if you toss the fair coin, therefore, the large amount of time, so 1 0 is missing, but yeah, you get the idea. So the large amount of times, it will come out roughly 50-50. And this is exactly the law of large numbers. And Monte Carlo simulation is supported by the law of large numbers, and it means only that the more samples you draw from your simulation, the better probability distribution you're getting. And the idea behind the Monte Carlo is, for instance, whenever you want to, this is a classical example, whenever you want to approximate the pi, number pi, and you will have, well, some square. Then inscribe a circle into the square, and then you start throwing darts in it. So basically you would have a uniformly distributed dots. And then you start coloring these dots into blue or red, depending on whether or not they belong to inside of the circle, so whether they're in the circle or not. This is done pretty easily with the trigonometry. Whenever you divide the amount of the blue dots by the amount of red dots, you get roughly the pi. And the more dots you have, the better your estimate is going to be. So obviously, this is also support for the law of large numbers. So we have generated the domain of inputs, which was like dots inside of the square, and then we generated the inputs over the domain and its probability distribution, performed the deterministic computation, which was calculating the amount of dots inside and outside, and then aggregated, which was like basically division operation. And now the Anglican. I have still 5 minutes, so I'm good. And should I start with a simpler example or with more complicated?
Simpler.
Okay, simpler example. Let's say that you have a Cassandra cluster. Cassandra is like highly distributed database, blah, blah, blah. For instance, imaginary, so DataStax would probably not be happy with the number, but one node, for instance, just all made up, can handle 10K requests, and the latency is normally distributed, which is not true in real life, and the mean would be 20 milliseconds, the standard deviation would be 5 milliseconds, and every extra request on top of the 10K per second would add the overhead exponentially. And let's model that. So we say that, okay, we have the blah, 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 the base amount of requests, all the closure code that you don't want to know. And then you basically take the normal distribution with the 20 and 5, which is basically the mean and the standard deviation, and then you add, depending on the overhead, so how many requests were on top of the 10,000, you add the overhead, and then you predict the latency. And then you start graphing these things because your boss is saying that your cluster is too slow, and you would like to know how many nodes you should have in your cluster in order for it to function completely fine. And for instance, the 5 nodes which are serving 50,000 requests would yield you some distribution pretty much like that, well sampled out of the sample base that or program that we just seen. For instance, you would have, well, roughly the mode around 20. And well, obviously, because it's closer to like 50k divided by 5 is roughly 10k, which is going to make it not entirely, not sit entirely on the 20. And then you kind of increase the load on your cluster. You say, okay, it's 5 nodes by 500k requests. And you start seeing that your latencies start drifting away. So you have like people who are waiting for 8,000 milliseconds, which is a long time for the user. If you don't want to lose them, of course. And then you start kind of balancing your cluster, adding nodes more and more and more. And then you find out that by 30 nodes, which are serving 500,000 requests, you are going to end up with roughly 20 millisecond response time for the cluster, which is very cool, and that's what you were aiming for. And now let's talk, I'll probably take maybe 3 minutes more than expected, half an hour, but you probably knew that I was lying anyways. Everybody knows what the flower is. Iris, exactly. And this is also very traditional example of like whenever you talk about classification or clusterization, most likely people are bringing up the iris somehow. And we're gonna talk in terms of Anglican, which is a probabilistic programming language based on JVM written in Clojure. It's well, Lisp language, and they're using the continuation passing style in order to, well, aggregate the state which is encapsulated within within your program, well, probabilistic program, and then each procedure is getting state and modifying it. You can modify it with the sample, or this is just, you say, okay, there was an instance of something that was happening, and then you can add the observation. You say that, okay, I have observed with a certain distribution the certain value, and then you say, okay, I would like to predict. I would say that there is a value with a certain label. So these are the 3, well, basic things which are mostly used in the Anglican. And then we define our data. So we have iris data, and we have, well, some features. I don't really remember which exactly is which. It's like the length, the width, or whatever. You can actually think of people just as well as iris. Just imagine that we're in the United States and it's inches or whatever. Even like it would be very small people, but still, just imagine it's small people in the United States. So the iris, and then we split the data into 2 parts. One is like setosa, and the second one is not setosa, which is the type of iris, obviously. So all you want to know from that slide that you have some like 1, 2, 3, 4 features, then you have a label, and then you have 2 sets of data where setosa is filtered from not setosa. So that's what we would like to predict in future. And then we are starting making some assumptions. For instance, we have some sigma, which is distributed with the gamma distribution, and we are sampling the gamma distribution and taking its square root, and taking that sigma and putting it into the normal distribution for our, like so to say, bias vector. So something that would be, we would be calculating our values against. And here, so assume it's just like, if you know Lisp, it's like let pretty much. So it's basically declaring some things in Anglican would be with assume. So you're making assumptions, so it's like defining the formulas basically. And then you have like the way you would, you calculate the dot product over your, well, feature set and compare it with the well, normally distributed with the distribution of gamma, well, 4 random numbers basically, and you will start training your data. What you do is you say that, okay, you take your array of data and you go through together with reduce through iris data with each one of them, and you say, okay, we are observing it, so we are modifying the internal state of the Anglican program, and we are, well, taking the flip based on the z, which is right over here, based on this. So flip is basically a Bernoulli distribution, so it would be either true or false. So flip would be returning true or false with the parameter z that we just calculated, and then we say that, okay, it is truly setosa or not setosa, and then we can, well, the time is up, and then we can predict the values. So we can say that, okay, I can say whether something is setosa or is not setosa, which is basically we just trained the classifier, which is well, predicting your iris or type of your iris flower. So if you'd like to learn more about probabilistic programming, these are just the highlights and the intuition that you probably, you wouldn't require it, but it would be kind of easier for you to start working with it, that all stuff if you already have some thoughts about or intuition about Bayes' theorem and about distributions. So you can grab all these books. It would probably take you only 4 months to read them. To be honest, I haven't read like each one of them from the beginning to the end. I highly advise the Murphy book, the top one. It's like, if you buy it, you will never regret. If you're interested in machine learning and data science, it's going to be like your handbook for the rest of your life, most likely. I wish you live long and prosper. It's a big book too, so don't worry. Bayesian models of cognition is something that Tenenbaum has written in, I think, 99 or whatever, so it also has a fair amount of the probabilistic programming examples. And Anglican, well, the language which I was kind of trying to demonstrate, even though it was hard in 30 minutes. And the introduction to Markov chain and Monte Carlo is very also nice book which has some intuition. I will also put the same slides online, so I mean, it's good you make photos of it. You can make photo of me. But yeah, thank you. And yeah, if you have questions, I will try to answer them, but I'm not an expert in the field, so I will just do my best. Questions? So good. I explained it all, right? Well, there are 2 outcomes, but I mean, usually people don't ask questions on my talks because they came for something they did not expect, but this time I think you were supposed to expect something like that. So yeah, I would like to invite Johannes.
So shall we make a break for 5 minutes?
Yeah, sure. Then we are making a break for 5 minutes, sorry. So we will now continue. Johannes will talk about church, basically, and yeah, he will tell you more.
Okay, so I will present some work actually also by Joshua Tenenbaum, which Alex also presented a little bit of, which is like applying machine learning to psychology, so to see how machine learning models could explain functions of the brain. So I will start actually with the book. So this is the book Probabilistic Models of Cognition, which presents the church programming language, which we already heard of. It's a probabilistic programming language based on Lisp. So if you look at the chapters, you can see that you can model a lot of stuff with this programming language. For example, you can model inference or inference about inference, or have hierarchical models. I think this is what Alex talked about. If you look at the repository of the language, which you cannot do right now because I don't have internet access, but whatever. So if you look at the repository, you can see that with the church programming language, you can like implement a lot of different machine learning algorithms. So like the standard thing that you know, you can also implement this in church. So one chapter is about generative models. The idea of generative models is that you have some kind of distribution and you try to model this distribution, and yeah, the idea is if you can model the distribution, you kind of understood what's going on. So that's why generative models are interesting. But I will just for a second go through the book, because I think what's very nice is that you have kind of a notebook environment where you can simulate the church language in your browser, and you can just read the text and do the examples, which is kind of nice. So the function flip we already saw, it just throws a dime, and so in this you just can run it. In this case we have tails, right? Okay.
Oh, that'll do.
That'll do, okay. So in this case we have tails. And you can run the experiment again, and we again have tails. And now we have heads, so everything is good. As you saw before, we can also just repeat this and also draw a histogram of the repeated experiment. So we have a coin which is flipped 1,000 times, and the histogram looked like that. And you can repeat the experiment, and the outcome will be a little slightly different. Yeah, because it's kind of an estimate of the bias of the coin. You can also model more complex stuff, like so here is just the product of two Gaussians. So the idea is you can take your simple distributions and just assemble them to more complex distributions and work with them. That's the basic idea. And then you can plot the density or do whatever. Okay, so let's go from flipping coins to simulations of physics. Okay, so what you also can do is to define kind of a world with blocks and simulate this world. This is all done in the magic function animate physics. So this scene is drawn randomly, actually. So the position of the blocks and the circles is random, and if you simulate it, you will just see, okay, that the circles fall down. If you run the script again, you have a different scene actually, and you can simulate it again. And yeah. Okay, so the next thing is this leads to the experiments which I show later. this is about the stability of configurations. So here you can see a random configuration of blocks, and the question is, will this configuration fall or not? So in this case, what would you say? Will it fall or not? Yeah, no. Okay, so it's not really clear, and yeah, it will fall. So that's how it is. Okay, so we can just run this again, so we get another world actually, and we can also say, will this fall or not? And so maybe, I guess this one will fall also, so it doesn't look very stable. So maybe let's try again. Okay, this one looks more stable, so I would say this one is stable. Okay, so it doesn't fall over. Yeah. So you can do this nice simulations in church. And also, what can be done? So the next step is just to say, okay, we have three different kinds of worlds. One is a stable world, one is almost stable, and one is unstable. So these are just fixed samples, right? Fixed worlds. We have a judgment function. Does the tower fall? So at the end, it just says, okay, did it fall or not, by just looking if the heights differ. That's the main idea. What we also have is this function noisify world, and the idea is that we take the fixed coordinates and we just shift them a little bit. So it's like, yeah, we just add some noise. And this will be important later. So we can either run the stable tower or the almost unstable tower or the unstable tower. And maybe I'll show you the stable tower. So this is the stable one, and this will never fall. And I can show you the unstable tower. So this one will very likely fall. Okay. And again, the almost stable world, actually. And this one, you don't really know if it will fall over or not. And if you start it, in this case, it doesn't fall over. So with our nice repeat function, as with the coin flips, we can just repeat this experiment several times and draw a histogram of this. And we see, okay, the stable tower doesn't fall over at all. The unstable falls all the time. And the almost unstable tower just sometimes, like in 30% of the cases in this time, this example falls over. Okay, so now let's go to the broadly this book has many examples, and you can just read about them, and the examples are from actual papers, and like the simulation of the physics engine is one of these papers, and the motivational example is what I showed you. Yes. Okay, so the basic idea is that you have stability of scenes, and we as humans are very good at judging the stability of scenes. So we can predict if stuff will fall over. We can see if this is stable. We play games, which is fun, just to see how good we are at predicting if the tower is stable or not. Kids like to play with towers, like maybe to train their internal physics engine, and also we have this kind of illusions, which are kind of astonishing, because this looks like it is very unstable, but it is very strictly balanced, so it's stable. And yeah, it's kind of surprising. Okay, so what kind of experiments did they do? There were 5 experiments. The first one, will the tower fall at all? So they showed a scene actually, and people had to predict if the tower will fall or not. The second one was a bit more complicated. In which direction will the tower fall, and actually. Then the third and the fourth one was also will the tower fall, and in which direction will it fall, but the object masses were varied. So basically people saw that there were heavier and lighter objects, and yeah, they had to predict if it will fall or in which direction it will fall. And then the fifth experiment is more about more complex scenes where you have a table with obstacles on the side and you have bumps on this table, so you have a more complex scene. Actually, that's the basic idea. Because the experiments will be shown to the subjects, but also you have the model which will simulate the same scene, and then you will kind of compare the variances of the subjects and of the model. And yeah, so that's why you have a variety of scenes to just see how good does the model work in different situations. Okay, so the IPE model, it's the intuitive physics engine. So the idea is that we as humans have kind of intuitive physics engine somewhere in our brain, and that you can like make an abstract model of this and implement a simulation and just see how good do the simulations match with the subject performance. So first we have inputs of the world to the model, which is the geometry, which means that the position of the blocks is just fed into the model, and with a little bit of Gaussian noise. So this is what I showed you before in the book, where you just have this noise adding thing. The second thing is that you enforce penetration constraints. That means that if the blocks are kind of have a non-realistic configuration, then they shift it a little bit until you have a configuration. Yeah, I don't know if this is somehow related to depletion force or if I have no idea, but maybe, yeah. So it's not a really uniform sampling. Okay, so then the intuitive physics engine is actually based on the open dynamics environment. It's like a common library you can just use to simulate physics. And it's a Monte Carlo simulation, which means just, okay, you draw your input and then you run the physics simulation. And the simulation is not run once, like in this trial, but it's run several times, like, for example, 10 trials. And in a certain amount of trials, it falls down, and maybe in a certain amount it doesn't. Depends on how stable the world is. Okay, so in the third step, you can ask the model questions. So the questions can be, will it fall? Actually, it just is the proportion of times the tower fell down in the simulation. So the more often the tower fell down, the more confidence does the model have that the tower actually fall. Second question is, in which direction does it fall? So it's just the average of the directions of the simulation. And what it also can do is predict how far will it fall, and this is like the supplemental experiments which are not covered. Okay, so this is what the subject saw actually, these kinds of scenes. And we have three different kinds of scenes. So the blue ones are the stable scenes, which are pretty much clearly stable. The violet ones are the scenes which are very difficult to predict. So it's hard to say if it will fall or not. It's not good to see here, but yeah. And the red ones are the illusional ones. So they look as if they are not really stable, but yeah, they are stable, like the stones that were stacked on top and balanced. Okay, these are the results of the experiments. These are the predictions of the model. and these are the predictions of the humans. And yeah, these are different scenes, what you can see. So each dot here is a scene. And they took these specific scenes just to demonstrate some stuff. Okay, so for the stable scene, the probabilistic model predicts that it will be stable, and the humans also predict that it will be stable. So there's a very good match in this case. Also, in the difficult to predict scene, the model could not really tell if this will fall, and also the humans could not really tell well if this will fall. But for the illusional scene, the humans predicted that it will fall, and the humans predicted that it will fall, and also the model predicted that it will fall, very likely, which is wrong, but yeah, that's the illusion. If you just compare this to the ground truth physics, which is a simulation of the physics without this adding of noise at the beginning, you can see that the prediction of the stable scene matches, and that also the prediction of the maybe hard to predict scene matches, but the illusion scene will be very accurately predicted by the ground truth physics. So this is like a strong hint that the IPE model captures something what humans do, and that this probabilistic simulation, yeah, is some aspect maybe, yeah. What you also can see is that the distribution, like the correlation of these two is very nice. So if you just make a regression line, this is very kind of nice. Yeah, for experimental data, it's good. And here it's very different because you have the mass of responses is in this direction. So the model is very sure about when things will not fall. So when stuff is stable. And actually, I think they chose this stimuli to pronounce this effect a little bit. But yeah, so the human prediction and the model prediction is different for the ground truth physics and fitted quite nicely for the IPE. So we have the same idea with in which direction will it fall, where people are shown like this kind of stimulus, and with this line they had to show in which direction the tower will fall. And if you compare the subject data with the model, with the probabilistic model, you have a kind of nice match, which you can see in this histogram. This is the difference between the model and the human. If you compare this with the ground truth physics, then you see that there's a wider spread. So yeah, the histogram is more blurred. The next thing is to vary the object masses. So you can see that the green objects are lighter, whereas the black objects are heavier. And also you have pairs of scenes, which are like the red one and the blue one. And the pair of scenes, they have the same physical configuration, but they have a different configuration of mass distributions. And yeah, what you can see here is the simulation of the mass-sensitive IPE. So they kind of, yeah, they had a parameter in the model which could account for the mass distribution. And if it's sensitive to the mass, then yeah, then the prediction with the humans and the model match quite nicely. If the model is insensitive to the mass, so it doesn't take the mass into account, then the correlation is not that good, first of all. And second, if you look at this pair of scenes, you can see that the mass-sensitive IPE can distinguish between the two, and that the mass-insensitive IPE obviously does not distinguish between the two scenes. Okay, so what do we learn from this? It's like people can, first of all, people are able to incorporate the masses of objects in this kind of scene predictions, and it also matches quite nicely with the model. Okay, so the last experiment is now taken on an even broader scale to make a more complex scene, just to test the model on another task, so to say. So in this task, the subjects had to predict whether more of the yellow or more of the red cubes blocks will fall down. And you have different kinds of tables. You have tables with like these obstacles, and obviously these obstacles will change the distribution of red and yellow blocks which fall down. And so you have different kinds of obstacles from different directions, and you can also change the height and the size of the blocks. These experiments were shown in two different conditions. The first one is uncued, which means that the bump could occur from any direction. So they were not told from which direction the bump could appear. And then there's a cued condition where there's also again a pair of scenes where you have the same constellation, and the bump could occur from two directions. Okay, so here is what the model simulates. Okay, so there are two things shown here. One is the direction of the bump that is simulated. So at this point, the model assumes that there's a 90 degrees bump, and the other one is the radius of the circle. So the farther you go out, the harder the bump is actually. That's the main idea. So as you can see from 90 degrees, this is from here, it's very likely that there will be more yellow blocks on the ground. Or if you bump from 180 degrees, which is from here, that's more likely that there will be red blocks on the ground. And yeah, so actually the model integrates over this range of degrees for this bump direction. So in the uncued condition, where they were not told, neither the model nor the humans were told from where the bump will occur, it was very hard for this specific scene to tell whether there are more yellow or red blocks falling down. So yeah, so the model and the human agree that they cannot really tell the difference. And if you look at the bump from 270 degrees from here, both the model and the human predict that there will be more yellow blocks. And if you look at the bump from this edge, actually both agree that it's hard to tell what's happening. And also, if you incorporate these obstacles, which makes the scene even more complex, you can see that in the uncued condition, both model and human say, okay, it's not really possible to tell whether there will be more yellow or red blocks, but yeah, maybe there will be a little bit more yellow blocks. But from the 180 degree bump, you can say, okay, there will be more red blocks, and from the 90 degree bump, you can say there will be more yellow blocks. So again, model and humans agree. Okay, so actually what I just told you, so I just told you about the one trial, and you can see the same thing here for like many different trials, and you can see that the correlation is nice for the cued condition and for the uncued condition, and that obviously if the IPE is simulated without obstacle, like it just ignores the obstacles, then the correlation is worse. And So also about these scenes, yeah, so it's insensitive from the scenes, which you can see that it really cannot tell the difference between the two conditions. Yeah, and even more obvious if you just do not take the obstacle and the cue into account, then the model and the human prediction do not match very well. Okay, so this captures that, yeah, first of all, humans can take these cues very accurately and nicely, and yeah, I think that's this here. Okay. So remember, the main hypothesis was that in the brain there's an IPE model which performs several simulations of the world and then takes the average of these things. And yeah, does this really happen is the question. And these plots can maybe give you a little bit of an answer to this question. So the idea is, if you look at the variance of the model for one sample and the variance of the humans for just one prediction, and the variance of the humans, and you assume that the humans just use one sample for the prediction, you would be on this blue line actually. And if the humans would take like 2 samples for the prediction, then you would be on this line, on the green line. That's the basic idea. And because you just halve the variance of the prediction. And also, so if you take the third sample, you will halve the variance again. So the regression will be on this line. Okay, so this is the basic idea of this analysis. And so you can see the regression here, and it's kind of parallel to the line with 3 samples. And in this case again, and here it's around 3, 4, whatever. And in the last one, you can see it's more near to 7. Yeah. Okay, so from this analysis, you can see that subjects typically use 3 to 7 samples per trial. Okay, to just summarize, the probabilistic IPE model can perform various queries on various scenes, even with varying mass and external forces, so it's very broad range what the model can explain, which is nice. It matches human performance more accurately than the deterministic simulations. So this is kind of the argument why you have several non-deterministic simulations, and most notable the illusion tower. So I think the idea is that the illusion tower itself is stable, but like the configuration is in a very unstable regime, and if you just wiggle a little bit, you have a tower which is unstable. And with this, yeah, if you just make different simulations around this tower, you will likely predict that it will fall. That's the basic idea. And also using, so if you buy this, that the brain performs different simulations, you can also make an estimate how many samples subjects use. Okay, and so like to conclude, probabilistic programming and probabilistic simulations offers a way to integrate symbolic reasoning and statistical inference to classically competing approaches to formalizing common sense thought. So it's kind of, you have symbolic reasoning, which is good old-fashioned AI, which you can do like this church language was very like Lisp, looked very much like Lisp, and also the scenes that you saw, they looked kind of this Schritt-Lu, which was done at MIT in the 60s or something like that. So this is so one school of thought, and then there's like the more modern machine learning on yeah, which is based on statistics more or less, and the two approaches kind of go together nicely in this framework of probabilistic programming. Yeah. So any questions? Yes, please.
So I mean, it's related to this quote, but for those of us who do not use functional languages, do you see, or where do you see the main advantages? Because I mean, obviously in Python you can also do both of these things, but does the functional paradigm give you something extra when thinking about sort of machine learning and probabilistic problems?
Yeah, I think, yeah, so like you have higher order functions, so the probability distributions, they are kind of higher order functions, so they are first class citizens, and you can think about them differently. Okay, so obviously you can do the same thing in Python, or just like load your library and do the stuff. It's not that you gain computational power or something, but I think it's very nice to think about in this terms. So that's why I showed the book, because you have like the notebook style programming in the web page, where you just can simulate stuff, and you can know this maybe from MATLAB or Mathematica, where you just have like a REPL and you can simulate stuff. And I think this is a very nice workflow which fits with this functional programming thinking. So I think this is why yeah, I like this stuff. Yeah.
Regarding the functional language, it's probably here very good because it runs very good in the browser. If you would put Python in the browser, it would be quite heavy-weighted.
But you can have IPython or Jupyter, that they look just as fine.
Yeah. True.
Actually, there was another, not paper, but another book, Probabilistic Programming for Hackers, which was actually using Python for actually exactly same stuff. So yeah, and they use Jupyter, and it works pretty nicely, so not that bad too. But yeah, I mean, I would say that because you're spending most of your time modeling, I would say that in many cases, the power of framework is more important than the power of language. So if the framework on the language that you're less familiar with can offer more things, like more distributions, better performance and stuff like that, then I would just bite a bullet and go with it. But that's just my reasoning. But I can see disadvantages in using functional programming even without knowing it. So especially with the Church or Anglican, it's all pretty intuitive, and yeah, it's more important to actually understand what's behind like how it's ticking. So the probabilistic programming concepts and the language itself is actually pretty much like 2 pages long. So it's like 20 constructs that they have, and the rest is hidden completely. Yeah, and they have like a bunch of different simulation methods, optimization methods. So what's inside is actually much more exciting. Maybe we can even make another user group about that one, because the way they implement the optimization over there is actually pretty crazy.
So thank you very much.